This presentation is for information purposes only and must not under any circumstances be considered to be an encouragement that you personally should construct anything based on this information. Your actions are your responsibility and yours alone. HHO is a common name given to the gas mixture produced during the electrolysis of water. Electrolysis can be accomplished by placing two conducting electrodes in water and applying a suitable voltage to those electrodes. For example, here we have a battery, and that is connected to two metal plates placed in a container of water. The result of doing that is bubbles of gas leaving the liquid. The volume of water doesn't appear to change much because 1 litre of water produces about 1,750 litres of gas. Michael Faraday did this and determined how much gas was produced per amp of current flowing between the electrodes. So-called scientists assume that Faraday's results are the final word on the subject. They aren't. Bob Boyce of America does not consider an electrolysis cell ready for use until it exceeds twice the performance of Faraday's experiments. We have a problem with the arrangement shown up above. The voltage which produces gas from water is 1.24 volts, and so if we apply, say, 12 volts to the electrodes, then that's very inefficient. This little green part produces gas, and this red part just heats the water. With 12 volts applied, 10.6 volts don't make HHO gas, and so the process is only about 10% efficient, and around 90% of the power applied only heats the water. We can improve on that, of course, by using two cells connected in a chain, or in series as it's called. The current flows through one set of plates, then on through the next set of plates, and back to the battery. Now that doubles the amount of gas produced, and it doubles the overall performance of the system, because with two cells, this amount, shown in green, makes gas, and this part, shown in red, which is smaller, makes heat in the water. With three cells, you get 3 times as much gas and a less amount of energy wasted in just heating the water. If you use 6 or 7 pairs of electrodes with a vehicle's electric system, it's about the most effective way that you can get to operate with a vehicle. However, water doesn't easily break down into HHO gas, and so using a catalyst is an important step forward. The two best known true catalysts are sodium hydroxide and potassium hydroxide. These increase the current flow through the water, and so increases the HHO gas volume produced. The optimum sodium hydroxide mix is 20% by weight, and for potassium hydroxide it's 28% by weight. However, these catalysts react with many electrode materials, and so 316L grade of stainless steel has been found to be a good choice for the electrode material. It's not realistic to use the electrode arrangement shown earlier due to its sheer physical size. Instead, all electrode pairs are placed inside one container, perhaps like this. You have a series of metal plates, all the same shape, used in the middle of this cell, and you've got 1, 2, 3, 4, 5, 6 cells which are all separately contained inside sealed containers in your case. The gap between the electrodes is 3 millimeters on each side, and that gives you 2 electrolysis cells in each of these divisions. If you add HHO gas to the air entering a vehicle engine, it's highly beneficial because it promotes the full burning of the fuel being used, and that offsets the need for a catalytic converter, as well as increasing the miles per gallon by anything from 20% to 100%, and only half of 1 litre per minute of HHO is needed for that. That process also almost totally removes all pollutants from the vehicle exhaust. Some people are afraid of HHO gas as they think it can explode. It can't. Water expands some 1,750 times to make HHO gas, and so if it ignites and returns to water, then it will be some 1,750 times smaller. That is, it implodes. That change in size is very fast, and it releases a good deal of heat. Now, a word of warning: do not, under any circumstances, ignite HHO gas in the open air, as the bang from just a cupful of the gas is so loud that you could damage your hearing permanently, and you could be deaf for the rest of your life. So don't go lighting HHO gas, although some people seem to think that's a great interesting thing to play with. Now, a very important device for working with HHO is the bubbler. The bubbler is a container filled with water to a depth of at least 5 inches, and the incoming HHO gas is passed through a pipe and comes out through holes in the bottom to give a lot of little bubbles which flow up to the surface of the water. There is a little baffle to prevent any splashes getting into the output tube for the gas, and the idea is that if you were to get flame coming in through the gas output tube and lighting the gas here above the water, it has very little chance of going through the bubbles in the water and igniting the gas in the incoming gas tube. It's a very simple device, but is very effective as a stopper of flashback in a system. The fact that HHO gas implodes leaves us with 2 options. One of them is to change the spark timing drastically so that the implosion sucks the piston upwards in what used to be a compression stroke. This isn't convenient, although it has been done successfully in spite of the valve operation changes needed. The second option is to change the implosion into an explosion, which is a good deal easier than it sounds. The trick is to use the heat of the implosion to turn water into steam, and the fastest way to do that is to add cold water mist or fog to the incoming air, because that level of water has a very large surface area for the volume of the water, and that results in what's known as flash steam, which produces a positive pressure on the pistons, just as a normal fuel would do. This means that you can run a generator like this one here without using petrol. The efficiency of DC electrolysis for use with a generator can be improved quite readily. The first step is to use an electronic pulsing circuit instead of just an ordinary DC supply. These pulsing circuits are sold as DC motor speed controllers, and they can look like this unit here. This one has a good heatsink bolted to the output transistor, a couple of integrated circuits to produce the actual action needed, and a variable resistor to adjust the frequency that the thing runs at, and then a row of connectors for the connections of the power in and power out. The unit shown there is able to handle 30 amps of current, and fancier units are also available. Bob Boyce of America is the most experienced person that I know of in the HHO field, and he stresses the necessity for careful electrode preparation before use. For this, the 316L grade of stainless steel electrode plates have all traces of oil, grease or other contaminants removed from them, and then they are sanded with grade 80 sandpaper in two directions, which are 90 degrees apart, in order to create tiny peaks on both surfaces of each plate. The first sanding direction shown here is horizontal, second sanding direction is vertical, and those cross each other, and that creates the little peaks on the surface of the metal. When that's been done, the plates are washed with distilled water, and all hand contact is avoided by using disposable gloves. After that comes the conditioning process, where the plates are put into the electrolyzer and current run through the whole set of plates for several hours using a 20% sodium hydroxide electrolyte, and for that process it has to be sodium hydroxide. The plates are then rinsed off with distilled water, and the process repeated until the electrolyzer performance is at least double that of Faraday. And more precise details for this process are given in Chapter 10 of the ebook, which is a free download. The rate of gas production can be increased by increasing the number of plates in the electrolyzer. Bob Boyce chooses to do it this way. He builds a very much larger electrolyzer, which contains 101 electrode plates, forming 100 separate cells of electrolyte inside his container. He has a 12-volt battery with 3 safety devices feeding a 110 volt AC inverter. Now that inverter produces 110 volts RMS AC signal. That is rectified using a 4-diode bridge rectifier before being fed directly to the electrolyzer. Now that produces 155 volts of pulsing DC, and you have 100 cells inside the electrolyzer, so each cell gets approximately 1.5 volts applied across it. The gas output from the electrolyzer goes through a bubbler, a one-way valve, and then a second bubbler, and finally through a particle filter before being fed to the engine of the vehicle. Now that is an effective way of producing a lot of gas, but it isn't really necessary for running a commercial generator without the use of any conventional fuel. The way that you can do that is fairly straightforward and easy to understand. You have a generator, which is a motor which drives an alternator. The alternators normally have 2 outputs. One output is 12 volts DC, and the other output is mains voltage at mains frequency, and that depends on which area you're in. In most of the world, the mains output is 220 volts AC at 50 cycles a second. In America, that is 60 cycles a second and only 110 volts AC. Anyway, in this case, the generator, when it's running, produces 12 volts, and that's fed to the electrolyzer, which produces HHO gas, which is fed through a pipe into the incoming airflow, which goes into the motor. So as the motor goes round, its pistons draw air in strongly from outside. Now, to turn it into an explosion rather than an implosion inside the engine, the water is fed through a Venturi tube into the airflow that goes into the motor, and that works extremely well. Obviously, you have to have some electrical supply in addition to this to get the electrolyzer actually producing gas before you try starting the motor. But that aside, you can operate practically any generator with that sort of system. The water droplets go into the motor through a Venturi tube typically, which is a very, very simple device which is used in perfume sprays. Obviously, some safety features are advisable, and while they make the overall system look more complicated, it really isn't. As before, you've got the motor and its generator and the mains output, and the 12 volts, instead of going directly to the electrolyzer on its own, go through a contact breaker in case there's any form of electrical short circuit, and through a gas pressure switch in case the pressure inside the electrolyzer rises higher than it should. If, for instance, this output pipe got blocked some way. If that happened, the gas pressure switch would disconnect the electrolyzer from its supply and the whole system would stop. The electrolyzer output goes through a bubbler into a pressure holding tank of only 10 pounds a square inch, because it has its own special release valve on the tank, then through a second bubbler, and from that second bubbler the gas flows into the airflow along with the water droplets into the motor. Now, the addition of the bubblers are a very sensible and practical step. It's normal for a system like this to be stationary, because the output is generally used in a house. If that's the case, then a local water supply can be attached. So you have your local water main coming in here with an ordinary float operated valve like in a toilet. That feeds water to the Venturi tube, and it also feeds water through to a water pump which is operated by a sensor and feeds water into the electrolyzer as it eventually gets used. There are also 4 one-way valves put on the various components here, and that prevents anything happening when the system is switched off and everything cools down. And finally, a particle filter is applied before the HHO enters the incoming airstream to the motor. Now, there is a need to change the timing of the spark, and the reason for that is that there's a slight delay between the spark and the combustion of a petrol air mix. This combustion needs to happen a few degrees after top dead center, so that it pushes the crankcase round, the crankshaft round in the crankcase, and spins the engine as it's supposed to spin. The problem is that because of the delay with the petrol hydrocarbon chain breaking down, the petrol engine spark occurs a few degrees before top dead center. So the compression stroke on a petrol vapor air mix is before top dead center, and the motor continues to go round while the molecules split into smaller particles, and it's gone round further again when the explosion occurs, pushing down and giving the power stroke. Now that's the way that the petrol engine has to operate. If you then just replace petrol vapor with HHO gas, then you have a major problem, because HHO gas ignites instantly, and that would be far too soon because of the way that the generator is manufactured for use with petrol. So if you have a HHO air water mix here on the compression stroke and you spark it at 8 degrees before top dead center like petrol would, then you will get an explosion at 8 degrees before top dead center, and the power stroke will tend to push the motor round in the opposite direction to the direction it should be going. Now that is a real problem, because that will quite probably break the connecting rod between the piston and the crankshaft, as well as doing other damage to the engine as well. To lower manufacturing costs as well, the spark timing is often taken off the output shaft, producing a spark on every revolution, instead of every second revolution as is actually needed by a four-stroke engine. These extra waste sparks don't matter with petrol, as they occur during the exhaust stroke. So the petrol exhaust stroke with the open exhaust valve is when the waste spark occurs with a petrol engine. The trouble is that's not the case with HHO, because with HHO you have to delay the spark until after top dead center, and that could be when the HHO intake valve is wide open, and when that happens the HHO ignites and feeds back into the feed to the electrolyzer, and you really don't want that to happen. So there are two things that we need to do. We need to deal with the timing delay, and we need to overcome the waste spark. There are various ways that this can be done, and each engine design is slightly different, so it's hard to cover every possibility. However, there is a technique which can be used with many engines and which deals with both issues at the same time. But before we get to that, let me explain one way that it can be dealt with. Most generator engines are four-stroke engines with intake and exhaust valves, which are probably something like this. You have the two valves operated by rocker arms, and the rocker arms are changed in position by push rods. The intake valve, shown here, is on the right. It's pushed down by a camshaft, compressing the spring and opening the inlet port, and that only takes place every second revolution. So if you mount a switch so that it opens and closes with the intake valve, and you remove the original spark wiring, then an adjustable electronic circuit can set the correct spark timing. That sort of delay circuit that you need for that is called a monostable multivibrator, and it's very easy to produce. We can use two of those circuits, the first to create a delay while we get the right timing for the spark, and the second to give a very brief pulse to the ignition circuit to actually generate the spark. But we don't have to do that. Selwyn Harris of Australia has kindly agreed to share detailed information on how he performs the conversion of a standard electrical generator, and here he uses a GX4000i generator as an example. His conversion deals with both the delayed spark and the waste spark. The first step of the conversion is to remove the fuel tank, which is held in place by 4 bolts, and that gives access to the carburetor, which is removed as it's not going to be used. This is a picture with the tank removed, and this is where the carburetor is normally connected. Now, the actual detail of the carburetor is seen more clearly here, and it's not a symmetrical face to the engine port there at all. Now the next step of the job is to construct a pressure release valve, and for this parts are bought from the local hardware store. The brass fittings are a 12 millimeter barrel, a 12 millimeter female T fitting, and a 12 millimeter to 9 millimeter hose reducer, as shown there. The PVC plastic fittings are 1/2 inch to 1 inch, 1 1/4 inch reducer, and a 1 1/4 inch end cap. The end cap gets drilled, as does a lot of the reducer. Also you need a roller ball from an old computer mouse. Now it may be difficult to get those nowadays because they no longer make computer mice with roller balls. So a 3D print version of one can easily be made if you can't get one from a mouse. You also need a fairly weak compression spring to hold the ball in place during the normal operation where the gas pressure is low. The cap is drilled with holes, and the components are assembled to produce a pressure release valve which looks like this. The inside of that arrangement is like this. You have the vent holes drilled all over the cap. The weak spring presses the roller ball down into the fitting here, and the fitting screws into the female thread brass T-piece. The ball is held in place by the spring, allowing HHO to flow through. But if a sudden increase in pressure occurs, then the ball is forced upwards, and the excess pressure exits from the system through the holes drilled in the plastic cap. Selwyn also adds an additional spring-loaded valve to the generator in case the electrolyzer doesn't produce enough HHO gas volume. He calls it a vacuum release valve, but it actually operates on reduced pressure rather than on actual vacuum. Selwyn uses an electrolyzer known as a Hogg electrolyzer. Its construction is shown in chapter 10 of the ebook, and he reckons that it produces something between 4.5 to 5 litres per minute of HHO gas, and that's sufficient to run this generator properly. So the arrangement is you can get air drawn in through this so-called vacuum relief valve if necessary to supplement the HHO inflow, though that is not normally necessary. The Venturi tube produces water droplets which get mixed with the air and pass through the female T junction, which forms the pressure relief valve, and on to the engine air intake. So that's a quite neat and compact system that is produced. Now for that, a piece of 6mm thick aluminium plate is cut and shaped to be the same size and shape as the carburetor gasket, which, as we mentioned, is not symmetrical. The pipes, backing plate, pressure relief and vacuum relief valves, gaskets, nuts and bolts are then assembled as shown here. The paint actually conceals the different materials being used. This is where the carburetor was attached, and this is your pressure relief valve, and this is your so-called vacuum relief valve, and this is the connection going to the electrolyzer. Now that's the way that the system is connected at the engine itself. You now need to take off the generator cover and the pull start cover. It's only necessary to undo 4 of the bolts in order to take the cover off. This is the cover here, this is the pull start, and these are the connecting bolt positions here. When you remove that, the engine looks like this. You have the rotating flywheel here. This is the transistor discharge ignition block here, and that's attached to its own plate, which is bolted securely to the actual frame of the machine, the actual frame of the generator. The pickup for this is arranged to be 8 degrees before top dead center so that it operates with petrol. We need to remove that and put in an aluminium plate to allow the TDI to be mounted in a new position, because we're going to burn a new fuel, and it's necessary for that to retard the spark. So to modify the ignition, we want to move it to top dead center. This is Selwyn's aluminium plate, ready for the timing change. Now that aluminium plate does get altered. He drills additional holes in it to let air flow through to cooling fins which are behind that particular plate. But that's just a detail of how the plate is completed. He also paints it black to make it look pretty. Now, he remarks that the intake to the carburetor is blanked off with a piece of tape, so you can't actually see it clearly in this picture. It's a good idea to cover openings when you're messing around with an engine, because it is extremely easy to drop something into an opening or to have dirt enter the opening itself. Now, the tools required for constructing these components are a drill press and a jigsaw fitted with a metal cutting blade. Selwyn used this timing alteration method on his own smaller generator, which has run trouble-free for a year. The objective in this alteration is to delay the ignition spark from 8 or 9 degrees before top dead center to either top dead center or 1 degree after top dead center. The reason for that is that this allows for a good spark which is on the compression stroke, and when the waste spark occurs, the inlet valve hasn't yet opened, and so there's no HHO gas in the ignition area. That is to say, the exhaust valve has just closed and the inlet valve has not yet opened. This results in a good compression stroke for the HHO gas and doesn't try to send the piston backwards due to premature ignition of the gas mix. The picture above shows the aluminium plate mounted and ready to accept the pickup, and the plate has air holes drilled in it in order to allow cooling air to flow over the engine fins behind the plate. Now, the TDI adapter plate looks like this, and as shown below, the support plate is drilled with the ventilation holes and the adapter plate is just resting on it. The adapter plate has got 3 holes, top and bottom, and that will eventually be bolted to the support plate when its position, its exact position, has been established. When it's locked in place, the timing never changes. In 2010, when adapting a previous generator, an experienced mechanic was asked to establish the TDI plate position, and he charged $60 for doing that. Finally, the covers and the starter handle need to be bolted back in place, but instead of paying somebody else to set the new spark timing, it's perfectly possible to do that yourself. One effective method is as follows. First, you mark the casing of the engine in a convenient location as shown by the yellow mark here. Secondly, you remove the spark plug and insert a long screwdriver until the top of the piston is felt. You then manually rotate the engine clockwise for this generator, as you can see from the curved fan pieces on the flywheel. You rotate it until the screwdriver is no longer pushed upwards. It may take more than one rotation to find that point accurately. When that point is found, mark the flywheel directly in line with the casing mark which you just made. This marking needs to be very accurate. In other words, the disc here, the cylinder here, has moved round further to the right. So the mark will be to the left of this yellow mark here. You continue rotating the flywheel very slowly until the screwdriver starts to go down again, and you mark that point on the flywheel. Again, this marking also needs to be very accurate. Now you measure the distance along the flywheel between the 2 flywheel marks which you just made, and then you make a larger mark on the flywheel exactly halfway between your 2 marks. If accurately done, this new point is where the flywheel is when the piston is exactly at top dead center, which is where we want the spark to occur. The marking on Selwyn's flywheel is like this. There's the start mark and there's the finish mark, and this yellow line is in the middle of those two. You need to work very accurately on something like this. The next thing is a bit of arithmetic. The diameter of the flywheel on this particular generator is 180 millimeters. That means that its circumference is 3.14159 times 180 millimeters, which is 565.5 millimeters. And as there are 360 degrees in each rotation of the flywheel, then the outside edge of the flywheel will move 1.57 millimeters for each of those degrees. The engine specification on this generator states that the spark timing is 8 degrees before top dead center, and we want the spark to occur at exactly top dead center, which means that we want an extra 8 times 1.57, which is 12.5 or 12.5 millimeters of the flywheel circumference to have passed by before the spark occurs. To achieve this major delay in the spark timing, the TDI sensor needs to be moved only 12.5 millimeters in the direction which the flywheel rotates. You will notice that for this major timing change, the TDI only needs to be moved just half an inch, and that's why your markings on the flywheel itself need to be very accurate. We're dealing in small amounts here. The next step is, when the TDI adjustment has been made, the timing can then be checked using an automotive timing light connected to the spark plug lead. For this, you take out the spark plug, connect the lead, and the engine can be spun using an electric drill. As the flywheel is spinning fast and the flash of light from the timing light is very short, it makes the flywheel mark appear to be stationary, in spite of the fact that it's passing by very rapidly. If the TDI adjustment is correct, then the central mark made on the flywheel will appear to be stationary and exactly aligned with the mark made on the casing. This is exactly what happened when Selwyn's motor had its timing adjusted. But the important factor is to have the spark close to top dead center point to make sure that the inlet valve is fully closed before the spark occurs. 2 degrees after top dead center is a popular point for the spark with many of the existing generator conversions which I've been told about, and that's possibly to reduce the loading on the piston's connecting rod. This is a photograph of Selwyn's latest generator conversion, having its spark timing checked out. An electric drill has been used to spin the flywheel, and the checking then is done visually with the timing device for automotive engines. Now, most small petrol engines have the spark timing set between 8 degrees and 10 degrees before top dead center. If it happens that you don't know what the timing of your particular generator is, then complete the flywheel marking procedure step 4, but make 3 additional marks on each side of the top dead center mark. Space those marks 1.57 millimeters apart, as they will then make a scale which shows each degree from 3 degrees before top dead center to 3 degrees after top dead center. When the timing light's used, it then shows exactly where the spark occurs, and if the engine had an original spark timing which wasn't 8 degrees before top dead center, then the scale shows immediately how much further the TDI needs to be moved to set the spark exactly where you want it to occur. Getting fine droplets of water into the engine can be done with a Venturi tube. A short length of 5 mm or 6 mm diameter copper tubing is used. This is generally available as central heating supplies, and if there's any difficulty in getting some, then your local garage can probably direct you to a supplier, if they don't just give you the few inches which you need from their own stock. This picture here shows you the female T junction of brass and the copper pipe. The copper pipe is heated with a plumber's gas torch and bent very slowly and carefully to this shape. Some people find it helpful to insert a length of suitable flexible material, such as the coiled steel spring material used to support net curtains. They do that before starting the bending, as that helps to keep the copper pipe from kinking when it's being bent. Next, the end of the copper pipe, which will form the nozzle, is filled with silver solder, and the end filed flat, and a small diameter hole is then drilled through that silver solder plug. The smallest possible drill bit should be used for this, although the hole may need to be enlarged slightly depending on what the engine requires in the way of water droplets. This is found out by successive trials. Finally, the nozzle is filed down to make a pointed tip. The Venturi tube is to be inserted into the last brass fitting. That is this brass fitting here, the female T-junction. So a 6mm diameter hole is drilled through the brass, and then the drill is, while still running, is drawn out of the brass tube slowly at a slight angle, the angle of drag being along the axis of the brass fitting, so that you can have a slight angle on the pipe as you push it into the brass tube. When it's positioned very carefully, it's positioned so that the jet is exactly central on the axis of the brass fitting, and when it's in that position you then solder the tube, the Venturi tube, to the brass fitting to make it a permanent connection. The way that you actually make the silver solder plug is you block off one end of the copper tube, and you fill the copper tube up with fine grained sand, and when you have it where you want it, you then fill the remainder with solder. Then you take the tape off the bottom of the tube and tap all the sand out, and you can use a pipe cleaner and other methods to make sure that every last grain of sand has been removed, because you don't want sand blocking up the tiny hole through the Venturi tube. The actual fitting of the Venturi tube in that is shown here in this photograph. This is the bottom of the tube. It then goes up inside the tube and ends pointing this way towards the engine itself. I suppose technically speaking people will grumble because I should be calling it a motor rather than an engine being restricted to trains. But I'm not bothered by little details like that, so tough. Now the generator should run well with 5 litres per minute of HHO, plus obviously air and water droplets. And you use a car battery to generate the HHO to get the system going if it's been left sitting unused for some time. In case these notes could be useful to you, you can download them free from this particular link here. They're under the name generator.pdf. The ebook, which has a lot more detail, is downloadable from this link, and it's called pjkbook.pdf. And that is the way that you can adapt an ordinary generator to run on HHO as the only fuel.